In today's lab, we're going to be studying what we call the Coulomb balance, which is really nothing more than the fancy name for a parallel plate capacitor where I'm able to change the distance between the two plates and I'm able to make some measurements on the forces on one of the plates. So you've probably seen a parallel plate capacitor before. It's basically defined to be any two pieces of metal that are much thinner than they are wide. And so I can talk about the area of each piece of metal. And if I take those two pieces of metal and I make them as parallel as possible, then I can create a nice homogeneous electric field if I hook it up to some DC potential. Right? So what is really happening when I attach these two plates to a battery is I'm accumulating some positive charge on the top plate, at least the way I've drawn it, at least the way I've drawn the battery configuration here, and some negative charge on the bottom plate. Now, of course, this is really just electrons building up on one side and therefore a lack of electrons on the other side. But of course, we always think about it as having a net positive charge on the top plate and a net negative charge on the bottom plate. Now, oftentimes in class, we study what's happening to the electric field in between these two plates, which is an extremely interesting phenomenon and something that we use a lot to study interesting physics. But here in lab, what we want to find out is what's happening to the actual plates because of the electric field that they've created. And if you study, say, the bottom plate, you can see, well, there's a bunch of negative charges that see an electric field. And therefore, there's going to be a force on those charges, right? They're going to want to move in the opposite direction of the electric field. And so there's going to be some electric force on that bottom plate because it's full of negative charges that want to move through the field. Now, in class, you'll derive what the actual expression for this force is. Today, we'll just give it to you. So the magnitude of this force, so let me use the same symbols that I'm using here. The magnitude of the force is proportional to epsilon naught times A, the area of either of the two plates, times the potential difference between the two plates squared, divided by 2d squared, where d is, of course, the distance between the two plates. And let me just draw explicitly delta V as the potential difference between the two plates. And so this expression is extremely interesting, and it helps me to understand what's actually happening to the two plates as they're creating this electric field. Now, in our lab, we're going to have to massage this equation a little bit because we're never actually going to be able to measure that distance d. The two physical plates that we have are going to be pretty close together, but we're not going to have a tool that's going to allow us to measure some absolute distance between the two plates. Now, what I'm going to be able to do once I have my two plates set up and make them as close as possible, right? As close as possible and as parallel as possible, I'm going to be able to take this lower plate and I'm going to be able to drop it down, and I'm going to call the distance that I drop it down z, right? But this systematic difference between the two plates, the initial separation z naught, is something that I'm not going to be able to physically measure. And since you've read the lab manual, this is why we have to take two sets of data instead of just one set of data, because one of my sets of data is going to allow me to measure the systematic, the distance between the two plates initially, and then another set of data is going to allow me to actually measure epsilon naught, which is the ultimate goal of our experiment. And so in terms of these two things, I can now say that the magnitude of the force on these two plates is going to be given by epsilon naught times A delta V squared over 2 z naught plus z squared, right? And now I have a nonlinear relationship between the force between the two plates and the separation between and my ability to change the separation of the two plates. That is the added separation of the two plates, which is the thing that we're calling z. So practically speaking, when I take all of my data, I'm going to want to measure z first, or z naught first, right? I'm going to want to be able to somehow calculate what this absolute distance z naught is, and then using that, I'm going to try to measure what epsilon naught is. So to measure what Z naught is, we're actually going to take this equation and we're going to do something called linearize it, or the process of linearization. This is one of the most powerful tools in data analysis that we have, because it allows us to take a complex fit, right, this nonlinear relationship between the force and Z, and rewrite it in terms of something that looks like a line. And lines are nice for statistical analysis because I'm able to do linear fits in a very powerful way, right, when I use origin. And in fact, there's more statistical power in doing a linear fit in origin than there is in doing a nonlinear fit. So if I take this expression and instead of solving it for f, I solve it for 1 over the square root of f, I get something that looks exactly like a line. Okay, it takes a moment to see it exactly like a line, but this is what we would have called y before. This is x, right? This is the slope, m, and this is the y-intercept, b, right? And so I'm able, when I plot 1 over the square root of f, versus z, I'm really plotting y versus x, and the slope of that line is this quantity here, and the y-intercept is this quantity. And so I can see that the thing that I want to measure first, z naught, is buried in the y-intercept of this linearized fit. So if I do that sort of pictorially, now I have an actual sort of I have my axes set up for what I might see when I measure 1 over the square root of 1 over root f versus z. I'm going to plot a bunch of points here, right? Okay, well 6. I'm going to fit a line to them, and when I do my fit, I'm going to get some y-intercept here, right? And that y-intercept is exactly going to be z naught times 1 over the square root of delta v. I'm sorry, 1 over delta v times 2 over a epsilon naught. Of course, the slope of that line is going to be given by 1 over delta v times the square root of 2 over a epsilon naught. And if you're staring at these two expressions, you can say, well, it might be really easy to get z naught if I just take the y-intercept and divide it by the slope, right? Because then all of my measurements of a and delta v and 2, they all cancel with each other, right? Because z naught can be calculated by just taking this y-intercept and dividing it by the slope. Once I have z naught, then I'm going to go back to my plot of f versus delta v squared, right? And of course, if I look at f versus delta v squared, I have a y is equal to a slope m times x, right? I have another line. I expect this line to have a 0 y-intercept, right? But now the slope of this line is going to allow me to extract what epsilon naught is. Okay. So now how do we actually do the experiment? So this week when you come into lab, a lot is going to be set up for you before you even get here. And part of this is because some of the wires that we're using today are a little more delicate than the wires that we used last week. But a lot of this reason is that most of the tools that we're going to be using are actually similar or the same as the tools that we're using last week. For example, you'll notice we have a digital multimeter that we're going to be, again, using to measure a DC potential difference. We have a power supply that's going to provide that potential difference. This one's a little bit fancier, right? And if you take a look at the dial, you can see that it actually has the ability to provide a much larger potential difference than the power supplies we were using last week. But you can see that we have banana plugs that are connected. We have wires with banana plugs that are going to connect our power supply to this box, and then we have wires with banana plugs that are going to connect this box to our digital multimeter. And so we're going to be using this again the way we did last week to monitor the potential difference that's coming from our power supply. Some of the things that are different, of course, rather than building our own circuit, we have a box that's going to take that potential difference and actually switch it over to two other wires that are going to connect it to our current balance. And these are the two wires that are a little bit delicate. And so that's why we set more of this lab up for you this week than we did last week. It also provides an extra fail-safe. This switch here on the box allows us to toggle whether or not the plates see the potential difference that the power supply is generating. And so that's going to be something that's important later. So the power supply is connected to the box. The box is provides a way to monitor the power supply and take that potential difference and apply it across these two plates. Now this is sort of where the magic happens over here, right? The actual current balance is the system that's of interest here. Because I want to show you some of the pieces, I'm going to take this top plate and I'm going to move it aside for just a minute, so that way we can take a look at what's going on with the bottom half of the setup. This aluminum plate is connected to one of the leads that goes to the power supply, and so I'm gonna put it off to the side again for another moment. This is an electronic balance. You probably have used these before, probably, I don't know, chemistry class or another physics class, or maybe some of you have something similar in your bathroom. But this is one of the tools that we're going to use to take data. I'm going to move it to the side again just for a moment so that we can get to the bottom, and then we'll build things up. One of the newer parts of this lab, for Kenyon at least, is this thing right here. So this is what's called a lab jack, and it's going to allow us the precision to move our balance up and down at very small intervals. And so you'll see inside of here, inside the lab jack, there's a thing that you can twist, and there's a label on it that says if you twist it one way it goes up, if you twist it the other way it goes down, and then there are a bunch of numbers. Okay, the lab jack actually has two different methods for raising and lowering. There's one that's the real coarse method, which is, well, it's not really coarse, but for the lab jack it's coarse. That's the one that we're going to be using today, where so on one side it says rotate up, on the other side it says Thor Labs, and there's a little line. On that little line, that little line is what you're going to use to be able to tell how many turns you're moving the lab jack up and down. There's also a way to turn it on the top, although that is going to be locked for us today, so we're not going to use it. It has a little Allen screw. Don't worry about this top one, but that would actually allow us to do some do some precision leveling. Anyway, so when I turn this, when I turn it in the direction marked up, it's actually going to raise the stage, right, by fractions of a millimeter. So each of it's labeled, if I start at 0. Now, of course, 0 isn't really 0. This thing is not at a distance of 0, but this is some calibration level 0. If I move it to 0.1 millimeters, what that means is that the stage has moved up by 0.1 millimeters, which means that the 10 tick marks in between that are not 0.1 millimeters, those are 0.01 millimeters, and so I have precision at least to 0.01 millimeters, plus some estimation of what the next decimal place is going to be. Right? So we have beautiful precision in being able to move this lab jack up and down, and therefore being able to change the distance between our plates with great accuracy. So it's a good idea when you put the lab jack down to orient it in such a way that you can see that little line. You won't be able to see it in the video, but I can look at it from this direction to be able to see that little line, so that when you move the lab jack up and down, you're going to be able to see how it moves. The next step is to put the scale or the balance on top of the lab jack, and then, in order for this to work very well, we need to make sure that this balance is level. Now, luckily, most of our balances come with a little level float on top of them, and so you can adjust the legs or use paper shims, but I think it's easiest if you have a balance that has adjustable legs, so that you can make sure that is exactly level. Okay? And that being exactly level means that I'm going to be more confident in my ability to to measure the distance between these two plates, right? We discussed a few minutes ago how important it is for the two plates to be precisely parallel with each other. And so by making this level, that makes it easier for the system to be precisely parallel. So I have it leveled. I have it leveled as best I can here. Now I can take the aluminum plate and put it down on top of the balance, and now I can move the upper plate to look as though it's parallel on top of it. Now it turns out that our eyes are actually pretty bad at at testing whether or not these two plates are parallel with each other. I mean, the way that I have it set up now, I can actually see by eye that these two plates are not parallel because one side is touching and the other side isn't touching. Luckily, there are lots of things that we can shift, right? There are three different knobs that I can use. One to raise it up and down, one to twist it like this, and one so that I can twist the PVC pipe. There are lots of different ways for me to adjust this so that those two plates are parallel with each other. Now, I'm not going to actually make them parallel because, after all, that's part of what the lab is today. And my point here is just to give you an introduction to the equipment that we're going to use. But I am going to move them far enough apart so that when I turn on the system in a moment, I'm not going to have those plates touching each other. One of the biggest safety features or safety dangers of this experiment is that if these two plates are touching, what I've intended to be a large potential difference across the plate has turned into a short circuit, which has allowed lots of current to flow, which will blow out some of the safety fuses that we have inside the power supply. So it's best not to allow those two things to touch. When you're doing this leveling procedure here, when you bring them very close to each other and make them level, it's best to take a piece of paper. Rather than using your eyes, to take a piece of paper so that you can tell when those two plates are level with each other. It's surprisingly easy to tell where the friction points are as you move a piece of paper in between these two aluminum plates. Okay. We have plenty of paper, so it's a great calibration tool. Okay, so how this is going to work, once you have the system leveled and set, you're going to need to turn on the balance so that way you can tell what is the force between these two plates going to be. Now, as we discussed last week, before I do any turning on of a power supply, I check all of the knobs to make sure that they're turned directly down to 0. For this power supply, our wires are connected to the right-hand knob, and so it's the B volts side. So this is the knob that we're going to be using to turn it up and down. There's a switch here that indicates which of the two sides you're going to use, and so make sure that switch is pointing to the B side. Let me get that in the frame so that you can see it. The B knob is here, and the switch that changes it is right here. Okay, so I have it pointed to the B side, and so I'm going to turn the power supply on. That would have been more dramatic if it actually turned on, right? There are two on switches. I forgot about that. There's this switch here turns the power to the entire power supply on. This switch is going to make it so that it's ready for DC, and then this light indicator here lights up telling me that it's ready to go. I'm now going to turn on my digital multimeter, which is a little bit out of frame, but I'm going to turn it on to measure a DC potential difference, just as we did last week. I'm going to put it up there. I'll let you know what it looks like. And now I can I can see that when I turn my potential up, I get a reading on this gauge here that corresponds to the reading that I'm going to see on my digital multimeter. Okay, so I'll leave this here so that you can see what the digital multimeter looks like in the frame. And now I haven't turned this very much, but it's already up to 54.5 volts, right? So that's a pretty big potential difference. And so I know that when that the potential differences that we're going to be using in this lab are actually ones I don't really want to touch this setup, right? Or if I touch the lab jack, I want to be very careful that I'm sort of avoiding this area. So just beware that these potential differences here, are in the order of volts that will give you a little bit of a feeling if you come into contact with them. That being said, right now the power supply is reading 54 volts, but of course the box has this toggle switch that's still set to open. And since this toggle switch is set to open, that potential difference is not being transmitted to the two parallel plates over here. Now, again, I've separated these by a lot, so I'm not expecting to see very much over here. But let me zero out the scale. Let me just show you what it will look like when you have this calibrated and when you have the plates where you want to. You will record what is the zero potential difference. You can then hit the toggle switch, and the potential difference, the force will change once the potential difference is being applied. Here, that changes not very much. It is in fact comparable, seems to be, to the variance of the wind blowing across or the natural air currents blowing across the scale. So I'm not seeing very much here. But when those plates are closer to each other, you're gonna be able to take that measurement. And every time you either change the potential or change the distance between the two plates, you're gonna want to measure both the reading on the balance before you turn on the high voltage and the reading on the balance after you turn on the high voltage. So that way you can find that difference, right, to actually calculate what the force is. So the two measurements, or the two series of measurements that you're going to be taking with this, are first setting some constant potential difference between setting some constant distance between the two plates, changing the potential difference here, making a set of readings so that you can calculate the force as a function of the changing potential. Then you'll take data where you set the potential equal to something, and you change the distance, and you have a set of data now where I have the force as a function of the distance between the two plates. And those are the two sets of data that we can take with this setup. So again, the hardest parts of the experimental setup today are making sure that the plates are parallel, making sure that you take readings of both the force that the balance, what the balance is reading before you turn on the potential and what the balance is reading after you turn on the potential, and then to make sure that you don't touch this when the high voltage is on. Okay. So to safely shut this all off, I'm going to turn this down to 0, turn that off, turn that off, turn that off, turn this off, and we're done. So I just want to leave you with some final thoughts. Now, when you set up this experiment, as I just showed you, make sure you set it up carefully. Make sure that the plates are as parallel as you can possibly get them, and that you've turned the lab jack down just a little bit before you actually turn on the 350 volts. 350 volts is a large potential difference, okay? And so if the plates are touching each other, you're gonna blow a fuse. Also, record your data very carefully. So read the way that we've outlined you to do it in the lab manual. You will end up with two sets of data, both the force versus potential and the force versus distance, although you're going to be taking that data you take that data interspersed with each other. So make sure you've read that section of the lab manual a couple of times so that when you take your data, you can do it once without systematic error. And make sure to record the zero potential every time you make every time you make a reading of the force. And when you have the power supply on, be mindful that the power supply is on. Don't touch the plates, don't touch the wires, don't touch the box, just touch the lab jack and the digital multimeters. All right, good luck.